Hey guys, welcome back to Material 685. Before I jump right into today's lecture, I want to say thank you for the feedback on how the class is going. I'm going to try, it seemed like the main comment was the videos are helpful, but you'd like them earlier in the day. I realized that this video is not posted earlier in the day. The reason for that, and the reason for the general lateness, has to do with the homeschool and just general misbehavior of my kids. It takes a while to get them through their assignments in the morning. And also, it's just my general preference to not get too far ahead of the class. I'd like to kind of keep the same ideas in front of my mind that you guys are encountering. And so it's easiest for me to kind of make these as we go. Although I hear your feedback, so what I'm going to do is I'm going to try to post 2 videos today so that you have tomorrow's video by the end of the day so that you can review that first thing in the morning. Actually, that's not going to be as difficult as I anticipated because this morning I inadvertently read Chapter 8 before I read Chapter 7, so I've already reviewed that material, and when I realized that I had to go back and basically start over, so that's another reason why this video is not coming out until later in the day. But that means tomorrow's video should be out by the end of today too. So, and I saw there's some homework questions, so I'll be addressing that here in Microsoft Teams shortly. So with that out of the way, I'm going to go ahead and set up for the notes. So Chapter 7 builds on what we talked about in the last video, Chapter 6 with mechanical properties of materials, and here the focus is on the main mechanism behind many of our mechanical properties of materials, especially metals, and that is dislocation motion. And the degree to which dislocations are impeded defines in large part the mechanical properties of a material, especially its strength versus ductility. And so the goal for this video is to explore Chapter 7, which goes into depth what we mean by dislocation motion and some of the ways that we can affect their movement. So the main part here, so in the mechanical properties of materials lecture, we talked about stress-strain curves and especially the elastic and plastic region. Remember, elastic deformation is just a very slight lengthening of the intermolecular bonds, but not any rearranging of atomic positions. Now, plastic deformation, we're talking about just the opposite. Here we are rearranging the atomic positions. And in crystalline materials, right, this is done by moving dislocations. And this sort of theory was developed, I think, in the 20s and 30s, 1920s and 30s. This was well before they had microscopes that they could observe dislocations. Remember, we talked briefly last time about the transmission electron microscope and its ability through the through diffraction of high energy electrons off of the crystal lattice to essentially image dislocations. But before they could observe them, they theorized that dislocations were responsible for plastic deformation because they were able to, through other experiments, estimate what the bond strength would be between any two atoms. And they could also estimate, how many atoms were in a particular volume of material. And if they said, okay, well, if we have this number of atoms and this number of bonds, and we know this is the bond strength, then that should give us a theoretical strength that would be, the number of bonds times the number of atoms, or the number of bonds times the bond strength of each atom. And they found out that the theoretical strength based on this approach was way higher than what they actually observed. And so that led to the development of dislocation motion as a mechanism for plastic deformation. It turns out that you're not, when you yield a material, you're not breaking all of those bonds. Right? You're actually breaking one at a time. And this allows atomic motion on an atomic scale that moves much like an inchworm, right? So an inchworm has many pairs of legs, and it picks up and moves one pair of legs at a time, and so you see kind of the bend in its back, kind of moving along its body until it gets to the end, and it's moved. Then it's moved every pair of legs, right, one at a time through a certain amount, and so as you move down the inchworm, right, it moves forward by like 1/2 the distance between each pair of legs, something like that, right? So this dislocation motion at the atomic level is very similar to this inchworm, where we have a dislocation. Remember, what we're talking about with a dislocation is an extra half plane of atoms that has been inserted in our crystal structure, right? So we have parallel planes of atoms, and here we just have a partial. And so this is a imperfection, right? A one-dimensional imperfection that we talked about 2 or 3 lectures ago in chapter 4. And there's energy associated with this, right? So we have a non-equilibrium interatomic spacing near the dislocation, right? We've kind of jammed those atoms in, and so these are closer than they would otherwise like to be. And across the dislocation, we have atoms that are kind of moving apart slightly to accommodate the extra atoms that are nearby, right? But these are a little bit longer than they would normally be. And so there is a tendency for them to want to return to that lower energy equilibrium bond spacing. And so if you apply a force, right, say a shear stress on 1/2 of this dislocation, right, that just adds to this natural tendency to want to move out of this higher energy dislocation scenario to a lower energy equilibrium bond spacing, right? And so the application of that shear stress can induce this bond here, say, to break to this atom and reform over here, which then provides an opening for this atom to break this bond and reform over here. And in an inchworm kind of piecewise fashion, right, this location can work its way across the crystal structure until it reaches the end of the crystal, in which case, right, you have no more dislocation and you have a step, right? So what I have is the movement of atoms, a rearrangement of atoms, right, which we call plastic deformation, via this piecewise movement of dislocations. And it can happen both linear dislocations, sorry, the term, my mind blanked for a second, and also screw dislocations. In either case, right, you end up with the same end state where you've produced this step, but this is more of a torsional shear force, and this would be more of a linear shear force. We still have bonds breaking and reforming one at a time. So where do dislocations come from? Well, they form during the creation or during the formation of the the crystal itself. So if you take a molten material and you reduce the temperature, remember we have this tug of war between the thermal energy present in the atoms and their vibrations and the interatomic bonding, right? And so as you reduce the temperature, right, you kind of tip the scales in favor of the interatomic bonding, and they start to bond together. But they are also less mobile. So it is an overall lower energy situation for them to bond in a crystalline structure. But they don't always have enough thermal energy to diffuse to where they need to be in time. And so oftentimes you won't form a perfect crystal, right? It will form the best crystal possible under the constraints of the thermal motion available and the time scales available, right? So that's why if you cool a material very rapidly, right, you will form crystal structure with many more dislocations than if you cool it very slowly, right? So we'll see this again often in the rest of this class as we study phase diagrams and thermal transformations, because if you want to create a stiff and strong material, cooling it rapidly will produce many of these dislocations. In addition to other strengthening mechanisms. And if you want to form a very high quality crystal, say for semiconductor use, right, which we'll talk about in the second half of this course, growing those crystals, right, is done under an exceptionally slow and very carefully controlled thermal process, right? Because you want to have plenty of energy for these atoms to move exactly where they need to be, so that we don't have these dislocations form during their formation. And even after solidification, right, you can create dislocations through plastic deformation, right? And this might be a little confusing. You might think, well, I thought plastic deformation was dislocation movement, right? And it is. And it turns out that, right, when they're moving in response to a shear stress, right, it's not always as neat as we might depict in a diagram, right? There will be grain boundaries involved. There are dislocations moving relative to one another, and so I kind of think of it as kind of, say, a big crowd trying to exit a room very quickly, right? You're forcing a collection to kind of go through, to rearrange quickly, right? And so that might not be the perfect analogy, but as those dislocations are moving through the material, right, they multiply. They create more dislocations. So plastically deforming a material is not only the result of dislocation motion, but oftentimes it actually results in more dislocation density, even though you might think that, okay, the deformation is creating these steps. But along the way, as this dislocation is moving through, it is leaving behind more dislocations in its wake. Another place that dislocations can come from is thermal stresses during cooling, right? This is related to the solidification that we talked about here, right? We have cooling, we have thermal stresses that develop because atoms can't get quite to where they need to be, and so there's a higher energy state there, right, which is a thermal stress. And so the densities can vary quite broadly. I mentioned a minute ago about high quality semiconductors having intentionally very low numbers of dislocations, very high crystalline order, and so you might have as low as as 0.1 to 1 dislocations per square millimeter on the surface of a semiconductor or in a plane, which, when you're thinking about atomic dimensions, right, is a very low number, or as high as 1 times 10 to the 10th in the same area. So we're talking about 10 billion times, 100 billion times more in the same area for a heavily worked metal, right? And when we say warped, what we're talking about is high amounts of plastic deformation. And so these dislocations are, they have a high amount of strain energy, right? When we say strain energy, what we're talking about is the energy that's stored in the lattice due to the distortion. Remember, we can go back often to that that energy curve, right? So at equilibrium, right, we're at the bottom of the well, and if you force it off of that equilibrium position, right, it has to go to higher energy. So when I have this dislocation on one side, right, I have the atoms are closer than they would normally be, right, and so this is in compression. So I've pushed off of that equilibrium position to a lower atomic spacing and moved up that curve to the left. And on the other side of the dislocation, I am pulling these apart because of the presence of these nearby extra atoms, right? And so I'm moving up that energy curve to the other side, right? In either case, it puts me in a higher energy state, right? So that's the strain energy that we're talking about. And it dissipates as we move away from the dislocation, but we kind of end up with this, what we call strain field, right? There's a certain region that is at this higher energy as before it dissipates, right? Because you can imagine as I move away from the dislocation, right, and this is kind of depicted here in this diagram, that the atoms are distorted less and less and less, right, until you get far enough away that it essentially is not distorted at all. Because of this distortion, it is the material itself can achieve lower energy if these dislocations spread out, right? If you have a certain amount of distortion, if you distort any one particular area of the crystal with one dislocation, right, that's a certain amount of distortion. But if you try to then jam another dislocation into the same area, well, now you're pushing it even further up that energy curve, and it would be lower energy to just say, well, just put this dislocation someplace else, right, in the crystal structure. And so by nature, the dislocations are repulsive, right? So they're going to spread out to try to reduce the total energy. Unless you have dislocations that are complementary, right, that are of opposite signs, in which case they can relieve the energy by co-locating, right? So if I were to have, say, an extra plane of atoms someplace over here, right, it would make sense for that dislocation to move this way, or for this one to move that way, in which case they would be co-located, and right, two co-located complementary dislocations would just annihilate. So I have extra atoms and I have a lack of atoms, right, and so they just kind of fill in, and you cease to have a dislocation, right? So you think about this scenario, right? Not every dislocation is going to end up as a step at the edge of the crystal, right? It might link up with another dislocation and actually annihilate. And here I've kind of tried to use some of the diagrams from Callister to kind of illustrate this, right? If I were to have the same type of dislocation here, if they move close enough together, right, you can see that the strain energy in the lattice is additive, right? So I've got a lot more strain energy, say, in this region because I have this location in close proximity to this location, right? And so, nature is always trying to minimize the energy, and so this is unlikely to occur unless I have so many dislocations that they can't get any further away from another, right? So as I increase the density, right, they have to be close to one another. And here I've taken this diagram, kind of flipped it upside down to show how they can be complementary and then annihilate. So here I have this extra half plane, and here I have a half plane on the other side, and so as they move towards one another, as they're attracted to one another, right, this high can fill in this low, and so on, and vice versa. Okay, so dislocations move, and that's how we plastically deform. Now, how does crystal structure factor into this? Well, it's the atoms that are slipping relative to one another, right, exist within a crystal structure, and so there's a difference in how atoms move depending upon how they're arranged, and we know that the arrangement of atoms, their proximity, their density differs from one crystal plane to another and from one crystal direction to another. And so the dislocations, right, they move more easily on planes that have the densest atomic packing. And if we think about at least the metal crystal structures that we covered in detail, right, there are two that have that are close packed, right? That would be face-centered cubic and hexagonal close packed. And if we look at FCC in more detail, right, we see that the close packed plane, right, is this 1, 1, 1 family of planes, right? So there's several equivalent, crystallographically equivalent 1, 1, 1 planes within that, but all of them are close packed, and they all form the plane within an FCC crystal that is that the dislocations can move most easily on, right? And so nature is always trying to do the lowest energy thing, and so we see that FCC crystal structures are most likely to slip along this 1, 1, 1 family of planes, and within that plane along a 1, 1, 0 direction, right? Because if you remember, the 1, 1, 0 family of directions is on the 1, 1, 1 plane, but it's along this close packed direction, right? So if I kind of take this plane, here's what I get. I see that I have close packed planes, so all the atoms are touching their nearest neighbor, and if I move in any direction right along a line of atoms, I see that they're all close packed along that line, right? They're all touching along that line as well. And so this forms what we call a slip system, right? Close packed plane in a close packed direction gives us a slip system. And if we compare one crystal structure to another, right, we see that if these slip systems are the mechanism by which dislocation motion occurs, then it would stand to reason that the higher number of these slip systems that exist in our crystal structure, the easier those dislocations would be able to move, and by extension, the more ductile our material would be, the easier it would be to plastically deform it. And so if we compare the face-centered cubic crystal structures here, metals that we know are fairly ductile, at least if you're familiar with these metals, right? Gold is especially soft, right? Copper is fairly soft, and aluminum as well, especially in its pure form. These are all FCC crystal structures, right? With the 1, 1, 1 close packed plane and the 1, 1, 0 slip direction, right? And so there are many crystallographically equivalent combinations of these, giving a total of 12 slip systems, right? So there's lots of directions and planes to slip on, and also there are plenty of directions for body-centered cubic as well. It's not a close packed close packed crystal structure, right? But there are dense atomic planes and there are close packed directions, right? So the body diagonal, for instance, the 1, 1, 1 direction, right, is a close packed direction. And so here we see that relatively ductile materials, especially iron, takes a BCC structure, and it has a large number of slip systems as well. And so we see here that for both these FCC and BCC examples, high numbers of slip systems equal ductile materials. Now, if we compare hexagonal close packed, which you'd say, okay, well that's a close packed structure. What's the deal here? And there are some directions, right? But because of that hexagonal structure, you don't have as many crystallographically equivalent planes, and so there are close packed, but there's just not as many slip systems resulting from that particular atomic arrangement. And so if we compare, we see here, we have titanium, right? Titanium is known for being strong, but not particularly ductile, right? Machining titanium, titanium is done by machining. It's not done by forming because it's brittle, right? It doesn't have very many of these slip systems. And so if we look first at single crystals, So if we have a single crystal, say of FCC, we're going to slip along these slip systems, which are not. So if we have a single crystal, say with the unit cell, aligned along this applied force, right? We would have the 111 at some angle relative to that applied force, and so what we're going to get is slip that kind of occurs, as say shifting. This kind of looks like shifting like a stack of pennies or something, right? So we get slipping along these slip planes, not necessarily perpendicular to the applied force. And so, what are the conditions under which slip occurs? Well, first you need to have, a slip plane, and if you don't have one, eventually, if you increase the force enough, you'll find one. But the minimum condition, right, is gonna occur where you produce what's called a critical resolved shear stress, right? So I mentioned when we're talking about complex states of stress in the last video that you have axial forces and shear forces, and different slices through your tensile specimen, right? Different planes are going to have different distribution of force between tensile and shear, and so what causes slip is shear forces, right? And so we're interested in the shear force, so it's the critical resolve shear force. So there's some critical shear force that will result in slipping along these planes, and it depends on the angle, right, relative of the slip plane and the slip direction relative to the applied force, right? So theta here, or phi, right, is designating the angle relative to the slip plane, and lambda is the angle relative to the slip direction. So we're moving along the slip plane in the slip direction, and so the shear stresses along those angles are important, right? And so the shear stress on that particular plane is going to be dependent upon the angle, right, relative to the plane that we want to slip on, and the direction we want to slip in relative to the applied stress. And so, the yield stress here, remember, yielding is where we switch from elastic to plastic deformation. That's where we start to move the atoms around, right? The yield stress here is going to be dependent on the value for this critical resolved shear stress and the angle of our slip planes. This has a maximum value at 45. The combination of these two angles, right, which says that, okay, the yield stress can be no less than, or no greater than. I guess if this was smaller, it would make this bigger. Yeah, I guess it must be no, can be no greater than twice the resolved critical shear stress. And so, right, this is how a single crystal would slip, right? And if you look at in Callister, I didn't clip it out for the notes, but if you look at Callister, right, there's an experiment, right, a picture of I think a single crystal of maybe zinc, where they have a single crystal of a metal in a rod, and they've pulled it, and they have deformed it so much that you can see these slip planes with the naked eye, right? It kind of looks like that stack of pennies that's kind of been pushed over to the side, like I mentioned before. So that's how single crystals slip. So what happens with a polycrystalline material, right? And this is probably more relevant because most materials that you're going to interact with and use, right, are not single crystal, right? That's actually a pretty specific case, right? Most are polycrystalline. And so how does slip occur here? Well, the answer is that it occurs the same as it does to the single crystal, right? Just for each individual crystal. You're still going to have slip on the most favorable plane, right, along a dense plane in close packed direction, right, corresponding to each slip system. However, right, you are going to be applying force in one direction only. And each of these grains is going to be oriented randomly with respect to the direction of the applied force. And so slip will only be favorable or most favorable for a small portion of these crystal grains, right? The rest of them are going to have to slip under non-ideal conditions. And by forcing them to do so, it's going to require higher forces, right? I'm going to have to put more energy in, more force to deform a crystal grain in a non-ideal direction, right? And also here, remember that the grain boundaries, right, these are still tightly bounded. And so as we deform, right, we are not reordering grain boundaries, right? The grain boundaries stay where they were, and so this is going to force our crystal to slip in a non-ideal way, which increases the amount of force and energy that we have to put into the system to produce this plastic deformation. And so we see here that the grains are elongated, right, in the direction of the applied force. And if we look close up, we can see that these crystal grains, right, if we polish it and then plastically deform it, right, we are producing these slip steps, right, that we saw here with a single crystal, just within each crystal grain, right? And because the atoms or the crystal is oriented randomly in each crystal grain, right, we see that those steps are aligned in a different direction for each crystal grain. And a bit of a side note, right? We talked about dislocations and then also about twins. So you can have a crystal structure where you have this kind of plane and direction specific mirror image, right? So there is I can form a twin boundary, which is a slightly different kind of crystalline structure where I kind of have two crystalline structures that kind of match up at the boundary in kind of a unique way. And so this is one way I can switch from a crystalline structure to a twin, and that produces a deformation, right? But it's not so much of a slipping, it's more of a crystal kind of reorientation, which produces a smaller deformation than slip does. However, it changes the angle of the resolving crystal, right? So I have kind of taken this and more rotated it rather than just shifted it. And that can have an effect because now I have a new angle, right? So before the twin, I might have had a crystal that was oriented in an unfavorable position relative to the applied force to allow slip to occur. But now I have changed the angle, right? So I might be in a better orientation with which to slip, right? So that might make slip more favorable. And you see twinning more often in crystal structures that are less likely to slip, right, as you might expect, right, the BCC and the HCP crystals. Okay, so plastic deformation, yielding, is produced by dislocation motion. So if you want to increase the stress that is required for yielding to occur, right, you need to keep those dislocations from moving, right? And this is the core, and I mentioned this, I think, in the last lecture, the core of why materials, especially metals, you see this trade-off between strength and ductility, right? You're constantly balancing, you make a strong material, it's really brittle, so you give up some of that strength to get back a little bit of ductility, right? And it's always a trade-off. And it's because it's kind of mutually exclusive here, right? Both the strength and ductility come from the same source, right? And so I can't simultaneously have lots of dislocation motion and very little dislocation motion. And so, right, you're going to make a choice. And to increase strength, right, what you want to do is you want to impede the dislocation motion, right? Because that is what leads to yielding. What I want to do is prevent yielding for as long as possible, right? To force the system to have very large stresses before it can overcome the resistance to that dislocation motion. And I can do this 3 ways, right? First, at least the 3 ways that are mentioned in Callister, right? First is by reducing grain size, and then by adding impurity atoms, and lastly by work hardening. Cold working or strain hardening, right? It's all the same thing. So first, reducing grain size. So grain boundaries, right, are barriers to dislocation motion, right? They impede it because if you have a dislocation that is slipping in one direction in a crystal, right? So I have atomic bonds that are breaking and reforming one at a time, and that extra plane of atoms is marching its way across this crystal. Well, what happens when it reaches the grain boundary? Well, now the grain boundary, the preferred slip direction, is at some other angle, right? And so it has to change direction. Changing direction takes energy. If I can reduce the grain size, right, the smaller the grains are in a given volume, the more grains I have and the more grain boundaries I have, right? So if I can make these grains smaller, then if I have a dislocation that's moving its way across the entire material, it's going to have to change direction more often the smaller the grains are. And this is reflected in a pretty well-known equation called the Hall-Putsch equation that relates the yield stress to this grain size, right? So you can see here that as the grain, so this would be 1 over the square root of d, right? So as the grain size goes down, right, as I'm dividing by the square root of d, the yield stress is going to go up, right, because I have more grain boundaries as I go to smaller grains. And the grain size is controlled by solidification rate, or as we'll talk about in a little while, recrystallization. Right? If I solidify more slowly, I get bigger grains because I have more thermal energy for longer to allow those atoms to move to the lowest energy possible, right? And that would be large grains. Secondly, you can impede dislocation motion by adding substitutional or interstitial impurities, right? We talked about this in the crystalline perfection lecture as well, and this mechanism is referred to as solid solution strengthening, right? Solid solution meaning, right, I'm forming a solid solution by adding these interstitial or substitutional impurity atoms. And these impede dislocation motion because if I'm adding in another kind of atom, right, it's not going to be the perfect size to fit right into that crystal structure. Now, if it's close, I can put a lot of it in there, and we already talked about that as far as the solubility limits. But even close is not going to be perfect. And if I have an impurity that is too small, right, then the surrounding atoms are going to move in, right, and go to a lower equilibrium spacing, a lower spacing, which increases the energy. And if it's too large, right, they're going to be pushed out, which is going to make the interatomic spacing higher than normal. Both of them, again, increase the energy of the situation. And it becomes more likely, right, that a dislocation is going to want to co-locate with one of these impurity atoms, right? It's going to reduce the energy of the situation in general if I have an impurity that is pushing atoms out, right? If it can co-locate with a dislocation, that helps to relieve some of that stress right here. If I have small atoms, then it's easier to put an extra half plane at that location. And over here on the right, if I have larger atoms, right, then it would be easier to co-locate those on the other side of the dislocation where I have extra space, right? That allows the material to reduce its energy even if it has both impurities and dislocations, right, if they co-locate. However, if I then apply a force and I want to slip these atoms, well, slipping, remember, is the movement of this dislocation, right? Well, it has found a little energy well, there's a little reduction in energy of the system by sitting right here, right? And so to move that away from that spot, I'm going to have to increase the energy of the situation, right? And that takes more input, more stress to move that dislocation. So adding these impurity atoms strengthens the material because it makes it harder for these dislocations to move. And lastly, we have work hardening or cold working or strain hardening, all the same thing. And here what we're talking about is multiplying the dislocations, right? So I'm going to plastically deform. I'm going to move those atoms around, and by doing so, right, those dislocations are going to multiply, going to form more dislocations, and they're going to repel each other, right? And I talked about this already, that they repel each other, remember, because the distortion is additive, and it can reduce the overall strain energy of the lattice by spacing them out as much as possible. But as they multiply and increase, right, they can't get as far away, and so the strain energy increases. And for the dislocations to move within that strain energy, right, they have to overcome the repulsion, right? So they are pushed apart, but they have to move closer, which takes energy for them to move across the material. So as I add more dislocations, my material gets stronger. And usually, right, we are going to deform a material anyways during the manufacture, whether we're bending it, or rolling it, or extruding it, something like that. We're oftentimes imparting lots of plastic deformation as a part of the manufacturing process, and we can get the strengthening of the material as a bonus, right? So typically we think about percent cold work as similar. I guess we talked about with strain as this percent reduction in energy and in area, right? So if I go from an initial cross-sectional area down to some final, right, I have a reduction relative to my initial as a percent, right? And so that's what we think about as cold work. And if you look at the increase in yield strength as a percentage of cold work, right, as I increase from 50, 60, 70%, right, I get a pretty drastic increase in the yield strength, right? Say for copper here, I'm going from 150 to 350, right, something like that. So over 2 or 3 times an increase there. Okay. And so this last thing, we talked about the grain size, right? So the Hall-Putsch equation tells us that we can increase the yield strength if we can decrease the grain diameter. Well, how do we change the grain size? Well, going bigger is pretty easy, right? Because materials want to have big grains anyways, right? Having big grains decreases the overall energy because grain boundaries are higher energy, non-equilibrium spacing type atomic separation regions anyways, and so if they can have fewer of them, that's a lower energy overall. So as long as there's enough thermal energy, the atoms will rearrange to produce smaller grains, right? Grains grow all by themselves, but that doesn't give you an increase in yield strength, it actually gives you a decrease in yield strength, right? So if we want to get back some ductility, right, we can just increase the temperature, allow the grains to allow the atoms to reorganize a little bit and get back some ductility, right? That can be useful, but not if we want to strengthen the material. To strengthen the material, we have to go to smaller grain size. Right, and here, before we move on, right, we have the grains growing, right, as we have diffusion of atoms across the grain boundary, right? So I would have a big grain that gets bigger at the expense of a small grain. And it's a thermal process and a time-dependent process here. So we can see here that the initial grain diameter and the final grain diameter, right, there's a rate constant here that grows with time, and then exponential. So I can see here that both a log scale, right, I would have growth of my grains more rapidly initially, right, kind of slowing down as we go. But temperature gives me big grains. But if I want small grains, that's a little harder. It requires more steps. So first thing you need to do is to cold work, right? So I'm going to plastically deform the material quite a bit, add in lots of dislocations, and store energy in the crystal lattice itself as this strain energy. And so I might end up with a crystal structure that looks something like this, where I have these elongated grains, I have all of these slip planes and these steps. I can tell that I've cold worked this quite a bit. And then if I increase the temperature enough, right, I can give these atoms that are not where they want to be, right? There's dislocations everywhere, the crystal structure is all jacked up. And so if you give them enough energy where they can move around a little bit, they're going to want to move and create grains that don't have those dislocations, right? And so I have so much energy in this crystal structure that if I increase the temperature slightly, maybe half of the melting temperature, something like that, it gives these atoms just enough to start forming new grains. And so I get nucleation of new grains all over the place within these existing cold worked grains, right? And they'll keep nucleating, keep growing until I've consumed all of the original material and I have many, many new grains, much, much smaller. And these are not cold worked, right? But they're smaller values, they're smaller grains. So I get a bump in strength because I have small grains, right? But I don't have the cold work. Now I could go ahead and cold work this again, in which case I would have kind of two mechanisms in my favor. And this is referred to as recrystallization, right? So I'm sort of resetting the crystal structure by storing that strain energy and then allowing them to rearrange themselves. And I can see here, right? If I start at the beginning, I've cold worked it a lot, right? So that gives me a high tensile strength and low ductility. Remember, it's a trade-off. As I increase the temperature, I get recrystallization, right? So no longer do I have as high of a tensile strength because I'm reforming strain-free grains, right? So I'm getting back that ductility, trading off the tensile strength, right? As my grains are getting larger, right? Eventually reaching kind of a steady state. And the recrystallization temperature is defined as the completion of this process in 1 hour, right? So this is heavily temperature dependent, exponentially so. And so, but for consistency's sake, they say, okay, well, we'll just say the recrystallization temperature is whatever temperature is required to complete this in 1 hour. If I were to go above that, right, I will recrystallize, it'll just be faster. If I go below that, I can recrystallize, it'll just be slower. And these recrystallization temperatures are usually on the order of 1/3 to 1/2 of the melting temperature, right? And this would be in Kelvin, right? So not in degrees C. So again, just if you don't remember, you convert between the two by adding 273 to the degrees Celsius to get the Kelvin here. So if you say 1/3 to 1/2, just using an example, say here for lead. We have the melting temperature, 327, so you add 273, that's about 600, and then the recrystallization temperature is right around 0, which would be, right, 270 or something, right? So that is less than half in this range here. And I think it's also interesting to note, I think this is a concept check in Callister, right? And so can you cold work lead or tin? Well, not at room temperature, right? Because look at room temperature. It's above the recrystallization temperature, right? So if you cold work lead and tin and then sit on a shelf, it'll recrystallize, right? You'd have to keep that strain energy in there, you'd actually have to put it in the freezer. Last thing I'll say here, right, is that the more you cold work, the less temperature you need, right? So here, in this plot here, I have recrystallization temperature as a percent of cold work. So you can see if I really cold work it out here, 60-70%, right, I need a much lower temperature than if I just barely deform it at all, right? So there's a certain amount of energy needed to move those atoms around, and I can either provide it through the strain energy in the lattice, or I can provide it through the thermal energy of the environment. Okay, so that's the end of my notes. The next video will be on failure mechanisms, chapter 8.